Hello. Today we will be examining a situation involving Newton's second law, and that is the motion with zero net force. In this video, we will observe a ball rolling on a single axis and observe the position versus time of that ball's motion using a program tracker. Later, a computational model will be built to predict the motion of the ball with zero net force. Before we begin looking at the actual observed results in the computational model, it is a good idea to predict what we think might happen in this instance. The formula on the bottom right of the screen is a formula derived from the more common form of Newton's second law, the force vector equals mass times acceleration. But the formulas are identical. The derived formula allows one to predict the change in velocity that is directly proportional to the net force applied to the system. In this case, the system is the ball. Looking at this formula, it can be predicted that the final velocity will equal the initial velocity because it is assumed that the net force is zero. Now it is time to test that prediction. As the video plays, it can be seen that on the top right of the tracker program, a graph showing position versus time is formed. Although the ball looks like it is moving in the negative x and y direction, the axes have been tilted so that the ball moves in only the negative y direction. As you can see here, as I put on the axis, the ball is only moving in the negative y direction. If the axes were to flip, the velocities would not change, just the direction in which they were going. The line would be reflected across the x-axis, and the graph would have the line now going up and to the right instead of down and to the right. In order to make predictions of motion, a computer model was built using Python. This computer model was fitted within the constraints of time and velocity, which were found using this tracker program. And therefore, the distance traveled that is predicted should be close to that which was observed here. The computer model was also fitted with a force vector of 0 in the x, y, and z direction. Here are some of the initial vectors that we used in Python programming. Initial ball mass of 0.15 kilograms. Initial position of 0 in the x, y, and z. Initial velocity of 0, negative 0.412, and 0. And of course, a net force vector of 0 in all directions. The velocity vector going in the y direction is negative because it's moving in the negative y direction, and it was calculated using displacement over time in the tracker program. Now is an important question to ask that just because the net force is 0, does that mean there are 0 forces acting on the ball? In this case, that it is true that in the observed case there are forces acting upon each other, yet the net force is still considered 0. There's a force on the ball due to gravity, which can be seen as the red arrow, but it is cancelled out by the normal force or the force exerted on the ball by the ground, which is seen here as the yellow arrow. There is also a force of friction from the air and floor, but it is considered to be negligible. This here can be seen by the light green arrow. Here it can be seen that the observed and predicted paths are very similar, proving that the assumption of 0 net force can be justified. Towards the middle of the graph, the observed path seems to be progressing a little slower than that of the predicted model using the program Python. Error in this observed line can be attributed to the fact that there is a small force against the movement of the ball. It is small enough to be considered negligible, but there is still a small visual confirmation of a net force. Through this experiment, it can be seen that there is no net force on the object, and the final velocity can be predicted to be the same as the initial velocity. The graph on the screen confirms Newton's second law, at least for movement with 0 net force.